G'day viewers, and welcome to an introduction to ESP-NOW. ESP-NOW is a protocol developed by Espressive Systems, and my name is Tony. ESP-NOW is a short packet protocol allowing data to be passed between Wi-Fi chips regardless of the chip's connection state to a Wi-Fi network. ESP-NOW is a manufacturer-specific vendor protocol and is compatible with Espressive's ESP series of Wi-Fi chips, including the ESP32, the ESP8266, and the ESP8285. This video, all the code examples will be based on the ESP32. Is ESP-NOW Wi-Fi? When the term Wi-Fi is used in reference to a Wi-Fi network connection, then the answer is no. ESP-NOW is, however, compliant with the 802.11 Wi-Fi standard. The standard has a class of data called management action frames. Action frames allow short formatted packets of data to be passed between Wi-Fi devices regardless of their network connection status. ESP-NOW uses a subcategory of action frames called vendor-specific action frames and vendor-specific protected if you are using encryption. Each vendor-specific packet has a vendor ID allowing the chip to filter out invalid packets. Will ESP-NOW interfere with my Wi-Fi? The short answer is no. With ESP-NOW being 802.11 compliant, it will happily work alongside your Wi-Fi connection. With that being said, if your Wi-Fi channel is already heavily congested, then it will add to your congestion. Can ESP-NOW and a Wi-Fi connection run at the same time? The answer is yes. The receiver is set up in both station mode and access point mode. The purpose of the access point is to allow the sensor to find the receiver by doing a Wi-Fi network scan. The network scan is only done at sensor power up or reset. The scan will return the receiver's MAC address and Wi-Fi channel number. This information is stored in the chip's real-time clock memory, which survives the chip's deep sleep power-saving mode, which is essential for battery-operated devices. When it comes to terminology, Espressive likes to use the master-slave terminology for its protocol. I do find this a little confusing as I'm used to master and slave when it is used with single-wire devices where you have one master and many slaves. With ESP-NOW, if you have 5 door sensors and 1 receiver, you have 5 masters and 1 slave. I prefer to use the sensor receiver model, so when we start looking at code, you will see references from both, as I have deliberately not changed the code from Espressive. So please remember that sensor equals master and receiver equals slave. I've written an Arduino library header called credentials.h that contains common code used between sensor and receiver and also allows me to use variables rather than actual data in my sample code when it comes to things like usernames and passwords. A copy of the header file template can be downloaded from my GitHub page and installed in the library folder of Arduino. Variables in credential.h are Wi-Fi SSID and password, MQTT host, port, username and password, ESP-NOW, SSID and password. The ESP SSID is a prefix and the receiver will add its MAC address to the end of it prior to advertising the access point. As far as your Wi-Fi network and other client devices like smartphones and tablets are concerned, the ESP-NOW access point is a standard access point which can be connected to like any other access point. The ESP-NOW sensors will never actually connect to the access point. They only scan for the access points to retrieve the MAC address and the channel number. The reason we set a long and random password is to stop other Wi-Fi clients from trying to connect to the ESP-NOW access point. The last item in credentials.h is a struct that contains the data that the sensor passes to the receiver, and it is a MQTT topic, MQTT payload, and MQTT retain flag. When the receiver receives this data struct, it decodes it and publishes it to the MQTT broker without any further processing. Okay, let's have a look at some code. This is the receiver project. In my Arduino projects, I use tabs for each module. This allows me to keep a better track of their code. In the main tab for the project, I keep all the includes, all the global variables, and the setup and loop routines. Let's have a look at the includes. We have credentials.h, which we've already spoken about. The ESP libraries, which are part of the ESP32 core. If you do not have the ESP32 core installed on your machine, there is a link below to the guy with the Swiss accent who has an awesome video on how to install the ESP32 core. The Wi-Fi libraries are a standard part of the Arduino IDE and are already installed. The ArduinoJson and the PubSubClient libraries can be installed by the Arduino Library Manager if you do not already have them installed. So the global variables are my hostname, which will be your Wi-Fi hostname, and your MQTT client ID. We have full ESP-NOW SSID, which is the advertised SSID for the access point that the client will search for. We have a reference to the Wi-Fi client called ESP-Client. We have a reference to the PubSubClient called Client, which accepts the ESP-Client. In the setup, we begin the serial, small delay, print our little welcome banner, and then we set up the Wi-Fi. In the loop routine, all we do is call client.loop, which is part of the PubSubClient. In our Wi-Fi tab, we have set up Wi-Fi. We call Wi-Fi begin, which all that does is turn on the radio, which is required to pull out the MAC address. We then call set my hostname. Set my hostname, we call the MAC address, which is a byte array of 6, and we then build my hostname and full ESP-NOW SSID. We serial print out the IDs just for debugging, and then we connect to the home network. When we connect to the home network, the first thing we do is Wi-Fi set hostname. Wi-Fi mode is set to Wi-Fi access point and station mode. We then call Wi-Fi begin, set the username and password. We wait for up to 5 seconds to get Wi-Fi connected. If we don't get it, we then reset the chip and start again. Here's where we pull out the local IP address. This is purely for debug purposes, so we can print it out on the screen, and then we call ESP-NOW setup. In the ESP-NOW tab, we have Setup ESP-NOW, where we initialize ESP-NOW. If that fails, we reset the chip and start again. We then call the ESP-NOW register receive callback method, and we pass it the on data receive routine, which I will come back to shortly. We then call start ESP-NOW access point, and to start the access point we call Wi-Fi.softAP. We pass it the full ESP-NOW SSID, the ESP-NOW password, and the current Wi-Fi channel. If the access point fails to register, we reset the chip and start again. Otherwise we call MQTT setup. In the MQTT tab we have setup MQTT, where we call client.setServer, pass it the MQTT host and MQTT port. We then call MQTT connect. In the MQTT connect routine we have result equals client.connect. We pass it the host name, the MQTT username and MQTT password. If the result equals true, we serial out connected to MQTT, and that is the end of our setup procedure. If, like me, your MQTT broker does not require a username and password, simply set those variables to empty strings in the credentials.h library header and all will work fine. So back to the ESP-NOW tab, and we have the onDataReceive routine, which is called by the ESP-NOW library when it receives data from another chip. The data passed to the routine is the MAC address of the chip that sent us the data itself, and the length of the data. For debug purposes, we extract out and serial output the MAC address and the size of the data. We then copy the data into the sensor object, and we then serial print out the values of the sensor object, being topic, payload and retain. We then publish that information to the MQTT broker and wait for our next packet. So the last thing to do now is program the receiver. Once the chip fires up, all the debugging code will come out on the output screen. So we have our system IDs, we've connected to Wi-Fi, our IP address, ESP-NOW was initiated successfully, we have successfully created a access point, and we are connected to the MQTT broker. And that's it for the receiver code. Okay, so let's have a look at the sensor code. In our main tab of our project, we have an external C call, and this returns the internal voltage reference of the ESP32 chip. In our includes, we have ESP-NOW libraries, Wi-Fi library, ArduinoJson library, and our credentials.h library header. For our global data, any variable that starts with RTC_data_ATTR will be stored in the ESP chip's real-time clock memory so it can survive deep sleep. If we call ESP restart or we press the reset button, then this data will be lost. So for our deep sleep variables, we have boot count, which tells us how many times the chip is woken up, and we have wake up reason, which is ESP wake up clause. If we go to our deep sleep tab, we can see what that is, and the wake up reason will be either 1 RTC-IO, 2 RTC control, 3 timer, and so on. What we are chasing for this project is 1 RTC-IO. For our ESP-NOW data, we have ESP-NOW peer info, which is called slave, and that holds our receiver's MAC address and channel number. For MQTT, our topic is ESP32/test button / and then we add the MAC address to the end of that at transmit time. For our setup, we have our usual serial begin. Then we pin mode GPIO33 int pull up, and then we initialize ESP-NOW. So we go over to our ESP-NOW tab, initialize ESP-NOW, we set Wi-Fi mode to station mode only. If ESP-NOW and int equals ESP OK, we then register our on data sent event with ESP-NOW register send CB. If it fails, we restart the chip and go again. Once ESP-NOW has been initialized, we call ESP Wi-Fi set max TX power and set it to 78, which is the maximum allowable according to the API. If the boot count is 0, we call scan for slave, which is in the ESP-NOW tab. In the scan for slave routine, the Wi-Fi scan networks call will return all visible access points, including standard Wi-Fi points like your home network. We will then loop through the results and search for suitable ESP-NOW access points. For this example, it will start with ESPX_, and if the scan returns more than one suitable access point, we will choose the one with the lowest RSSI. At the top of the routine, we have a Boolean value called slave found equals false, and we set this to true when we find our first suitable access point. Current RSSI value is set to -200, and we set that to the RSSI value of the first suitable access point when we find it. Scan results is the results of the scan network call. If the scan result equals 0, we restart the device and go again. Okay, here is where we loop through the scan results to find a suitable access point. The suitable access point will have an SSID that starts with the ESP_now_SSID variable. When we find our first suitable access point, and in this demo we will only find one, we set the slave channel equals the Wi-Fi channel of the current access point. We set slave encrypt equals 0, and we set slave peer address to the MAC address of the current access point. And that's it for scan for slave. Once scan for slave is complete, we call the put me to sleep routine, which is in the deep sleep tab. Here we call the ESP sleep enable ext0 wake up routine. We pass it GPIO 33 and we set it to low, so the chip will wake up when you press the button. We increment the boot count by 1. This loop is merely a housekeeping routine that prevents the routine from going any further if you have the button already pressed. A small delay, and then we put the chip to sleep. If you have used the sleep routine on the Atmel series of chips like the ArduinoUno, you will be used to the routine returning back to this point when it comes up out of sleep. The ESP series of chips do not do that. The ESP series of chips will return to setup when the chip wakes up. If boot count is greater than 1, we then set the Wi-Fi channel to the same channel as the slave. This is very important, as in station mode, the chip generally comes back up on channel 1, expecting to have that change when you connect to a access point, which we don't do. We then call manage slave, which is in the ESP-NOW tab. I won't go through the manage slave code, as it is copied directly from the ESP-NOW demo from Espressive, and it is simply a housekeeping routine. We then call the print wake up reason routine in the deep sleep tab, and then if wake up reason equals 1, which is a GPIO wake up, we call the send button press routine, which is in the MQTT tab. We create our JSON buffer. In our JSON buffer, we add the root object. Then in the root object, we add an element called button, and we set it to 1. We add an element called VCC, and we set it to the value of the getMyVCC routine. We then tell root to print to sensordata.payload. We create an array the size of sensor data. We copy sensor data to the array. We set our peer address to slave.peeraddress. We then call ESP result equals ESP-NOW send to peer address, the byte array, and the size of sensor data. Now here are the possible values for result. What we're hoping for is ESP OK, but even if we get ESP OK, it does not mean that the receiver has received the packet. It merely means that our chip was able to transmit the packet. If the receiver receives the packet, it will return back a response, which we find in the receive data routine. When we send a packet, the onDataSent event is called and returns the MAC address of the receiver and the status of the send. If the status equals ESP-NOW send success, then all went well and we put the chip to sleep. Otherwise, we wait 2 seconds and restart the chip and start again. Well, that's pretty much it for the sensor code. I've already uploaded the firmware and let the device start up. And here is our result. We have our ESP-NOW in success, scanning for receivers, 5 access points found, SSID ESPX_240 is the one we're looking for. The other 4 SSIDs are both my home Wi-Fi network and my live ESP-NOW sensor network in my house. Now let's have a look at the big picture. Okay, so this is a alpha version of an MQTT Windows logger that I've written, and what it does is it logs the receive date, the topic, and the payload. It then divides the topic up into each of its individual sections, so we can group, sort, and filter based on each section. Now, I've written a filter for our test button and the son-off device that the test button will control. And here we have the base information. I will go ahead and clear the logs and press the button. And you'll see the ESP32 test button MQT comes in from the receiver, and then we toggle the son-off device. Okay, let's have a look at everything. This is an ESP32 programming jig with a Room32 chip in it, and that will act as our receiver. So I will start it up. This is an ESP32 programming board that I designed and built, and it will act as our sensor, and here is the mighty button we need to press. And I will reset and power him up. Over here we have the S26 son-off. You probably won't be able to see the light at that angle, but that's about the best I could do. But it is powering this, which is just a test downlight. Now, when I press the button, the downlight will toggle through MQTT. So I will clear the outputs so we can see everything come through. So when I press the button, the chip wakes up, sends to the receiver receives it, sends it into the MQTT, and the MQTT toggles the lights on. If I hit the button again, it turns the light off. And that's pretty much it. I would just like to say thank you for watching this video. I must say I thought I could whip it up in a couple of hours, but it has taken me several days because I'm a complete noob and as nervous as anything. Please like and subscribe if you're interested in seeing any more videos. My next couple of videos will be about the boards I've designed and built for my ESP-NOW projects. These boards will include my door sensor, my 6-button remote control, my ESP32 dev board, and a Sonoff ESP2 friendly USB to serial converter. You will find a link to my GitHub page in the description below so you can get the code for the projects in this video. Thanks again for watching.